and dot dl, and dv is v is the potential. Potential equals to w over q. So that is how you get this one. And this is dv. dv is a very small fragment, okay, a segment. So I need to integrate the dv from point 1 to point 2. Okay? So v21 equals to v2 minus v1. Okay, just remember the direction. 2, 1, 2, 1. They have corresponding relationships. And that is this part, just substitute here. Okay? V21 is the voltage potential between point 1 and point 2, but because this is V21, so it is the work from 1 point to 2 point, the P1 to P2. That is the integration goals.
First I thought this one 21.
Sorry?
First I thought this one 21. It's not 21, right? Like
No, this is not 21.
Yeah,
No, this is not 21.
This is
V21, okay?
Why
From
21
1
coming
to
here?
2.
Yeah, understood. Yeah.
Okay?
Thank you.
It's okay. So, let's see what this is. This is Kirchhoff's law, KVL. Okay? So basically KVL is the interpretation of the Maxwell's equations, but you just need to understand this. This conservative or irrotational field, assume V1 is 0 at infinity. You see? V1 is 0 at infinity. So most of the cases we get a V1, this one is 0, so V21 just equals to V2 for some of the cases, when the reference point is to infinity. I guess this one is very basic KVL. Do I need to go through this? KVL? KVL
Knowledge, but oh, it's some knowledge, but page 24, first step. Okay, next.
This one,
Yeah,
V2E. So this is the equation. Very important first step, okay?
Yeah, first step.
Yeah, this E field equals to minus gradient of electric potential. Gradient. This one is gradient. Gradient should be applied to a scalar. Okay? So E field is this one. Oh, that is because the first one is minus E dot dl. That is the formula we get previously.
Yeah.
But the second one, dv equals to gradient v dot dl. This one is basically a mathematical interpretation. Mathematically. First one is the physical meaning, and second one is mathematically, so that I can compare them so that I get this formula. Okay? So any loop, so this one is closed because it has a closed loop. I just integrate them. The first one, right? Integrate the first one. This one equals to 0. That is because the KVL. In the closed loop, the voltage potential should be 0, right?
Yeah.
Plus, and then the minus, and then it reaches 0. That is why this one 0. So this is any loop, and this one is Stokes' theorem. See, loop area, Stokes' theorem, loop and area. So this one and this one, they are the same thing because of Stokes' theorem. And this one just compare, so this one is 0. And then I can calculate that divergent of curl of E equals to 0. Okay? Curl of E equals to 0. Define scalar potential by a null identity. Okay.
The 0 have a dimension.
This one has direction.
Curl of E.
Curl of E.
The 0, why the
Why
0
is
vector?
the direction right? Oh, because this one is the direction. This is vector, right? This one is vector. So you need a vector dot a vector. So this one should be a vector. That is why you have a direction. But it doesn't matter. It's a very small deal. Okay. This one is while null identity. So just you can see there's a 1 and 2, right? This is just a two-way how you get this equation. The first equation is we just compare. The second equation, the second way to get the same equation is we get this first, and then we can get this one via the null identity. You know the null identity? Null identity is curl of gradient of a vector equals to 0. Gradient. called non-identity. This is one. This is for if you go to the higher level class, then this is how you get the Helmholtz equations. Okay. So negative sign by convention, so as to obtain positive V values. Doesn't matter. Lifestyle equation. Okay. Electric potential. Gauss's law for any volume of distributed charges. So this is what we get previously. Right? Recall. This is what we get previously. Right hand side Q, left hand side something like. Left hand side we get closed surface, and then we get D dot A dA, right? We get the formula previously. This one, right? Left hand side, right hand side. But now we just substitute the D with epsilon E. That is how we get. That is how we get this one, epsilon E. Epsilon E. So this is D in the previous case. Left hand side, right hand side, and right hand side is this is V rho dV. So the rho is the charge density of a volume, and then we just simplify this one. Okay, because the epsilon is a constant, I just divided the epsilon on the right hand side. This is the left hand side. Okay, this one is because the divergence theorem. Okay, this one equals to this one divided by epsilon, and then apply the divergent theorem. That is how you get this one, and this one is really important again. Okay, need non-integral version for application to any particular point. So because they are all integrated in, against the volume, so the inside they are the same. Okay. Because so E we can substitute with the minus gradient V, minus Laplacian V. Laplacian, okay, Laplacian V. So we just substitute, and then we can get this, this two. So partial differential equation requiring boundary conditions. This one has portion equation. This is Laplace equation. Don't recall this.
No solution.
No faster.
Then which one is five star? This one is five
This is
star.
not five star. This formula important. The boundary one.
This one.
No, just not boundary. Box portion equation, Laplace equation. Yeah. This one is a important formula.
Partial differential equation requiring boundary conditions.
We just talked this is a Laplacian operator.
Just
Yeah,
important.
just referring to the formula.
Yeah, that's all.
Oh.
No, five star. Important only. That's why I never say five star.
Okay.
Skip, I know skip. Important is it.
Okay.
একটা প্রশ্ন আছে কি এটা ভাগ্য আছে পরীক্ষা ভাবে দিতে পারবো
This is just a calculation.
Yeah, no need to discuss.
we can see page 27
The examples should I go through?
No need.
example no need
Okay. And then electric potential of materials. This I remembered. I said epsilon, mu, permeability, permittivity, and this is conductivity, right? Homogeneous do not vary from point to point. That means if a material is homogeneous, then the property of the material doesn't change along the distance or along the position. Isotropic means independent of direction. Crystals are not isotropic. I don't think this is going to be tested. Is that it? Going to be tested?
No.
Conductivity, I give you some examples. We don't care.
Go
About this
page 39 is 5 star
39. Right?
yeah
In 33 or
33 also has
33 Ohm's law.
that one is the equation
Okay. Anyway, this is the current. This is the introduction of the current, and you can see the constitutive relationship here. J equals to conductivity E field. This is how I write that. So let's go to the 5 star thing. So this is Ohm's law. J, okay, that's the equation. perfect dielectric. Perfect dielectric means the conductivity is 0, right? Perfect dielectric means conductivity is 0. If it is perfect conductor, that means dielectric infinity. It is infinity, but the E field is 0. Okay? Now V12, so it's V1 minus V2. V21 is V2 minus V1.
Yeah.
Okay? So this one is from 2 to 1. From 2 to 1, so 2 is there, and 1 is from the upper, right? And then it's minus E dot dl. This is the formula we mentioned, right? Then the E, I get the direction out, and this is amplitude, only amplitude. And the L because it's this direction, so this is direction, and this is the magnitude. Then I get EXL. So I equals to J dot ds. This one is to calculate the current, because J is the current density, similar to the rho. Rho is charge.
First line the E dot dl, and how to become x head E, then dot x head dl.
Okay. E is a vector. Vector has a direction and a magnitude. This is the direction of the vector. This is magnitude of the vector.
Okay.
For this case, x is the direction of this vector. dl is the magnitude of the vector.
Then get EXL. EXL. Then finally get EXL. How?
EXL.
Finally,
Because it only has the x direction.
Mm.
Just no notation tell you that E only has x direction.
Okay.
Okay.
Integration?
Integration, no.
No do integration or what? No. Is it done in integration right? Then only get right. How to get EXL?
First of all, the E is a constant. I just took it out.
Yeah, okay.
Right? That is EX. L is the integration from x2 to x1 and then dl. Just the
E like constant, right?
E is constant. E is
XX1.
independent of dl.
So DL. Okay.
Okay?
Okay.
So I equals to J dot ds integration over a area. So this is a current density over a surface. So it is dot ds and then integrate A. Similar to rho, right? Rho is a charge density, J is a current density. Then this is how I get the current, total current. Then J replaced by this one, and then I can get this. So this is Ohm's law. Ohm's law is resist R equals to V over I. So like the resistance is to evaluate the ability of a certain material to stop charges. So V equals to V12. That is this one. Substitute. I is this one. Substitute. Then I can get rho R equals to L over epsilon A. Okay. So let's see what is on this box. This box is, I think, this box is just direct substitution. That one is this two substitute, but this one is these two substitute. Okay? Am I too fast?
No, it's okay. It's okay.
Okay.
What's the formula for the surface area of the cylinder? I don't remember the formula.
You mean this one? What?
那个 cylinder 的那个圆柱体的表面积是什么？
The side area of the cylinder, is it? Side area of the
DS
cylinder.
DS 是指那个surface。
You mean this case?
不，就刚刚那个。
This case.
第二个
What is A, right?
DS 嘛 ，DS 是求它那个 surface。
Yeah.
It is two set of.
Yeah, the two sides, the two round, the two circles.
怎么算
E dot ds. So
？2 by R 啊。
pi r square.
Oh, pi square. Pi square.
So the S is the area that the electric field will go through, right? The electric field only goes through this one and this one. So the area that the electric field will go through is the two circles at the sides. That is pi r square. Okay. So any questions? Let's see dielectric. Dielectrics, you can see. For dielectric materials, then the charge can reside on the inside the materials everywhere, right? So let's see what's this.
派 r square，因为派 r 是1个就2个。
派 r 是等于两边的侧面积。
那不是2个2派是
对，这不是侧面积，
2个，
这个是侧面积。
是2个。
This one only.
Is that not it?
This one only just 3.
So go 39, page 39.
Boundary conditions. Yeah, boundary conditions.
Oh, for the case, I need to say something, okay? So for this one, the current we calculate, we use this
And
form.
who will be doing it?
We write I equals to A, and this is J dot ds, right? Write like this. I have Q ds.
You should know it.
Okay, this is charge, this is current, and we can use an analogy. Okay, for this one, that is, we have a material and we know the surface, we know the area, and we say it is A. Okay, so this is A. So if I tell you the rho S, that is how much charge you have over a surface, then we can calculate Q. For this one, what is JS? JS is how much current you have over a area. Then for this case, this one is the cross section area. There's no left side or right hand side. The A here is the cross section. It's just a pi r square, just the cross section.
Pi r square. 可是2个面是吗？
There's no two sides. This one means what does JS mean? JS means how much current you have over an area. For the whole thing, this JS is defined to the cross section.
派 r square 是不是主面积嘛？点面积。横截面的那个。但是有一个讲法说那个，如果是 DC 的话呢，就是表面积是那个就 surface； 如果是 DC 的话，就是那个侧面积了。
什么时候是表面积？
If a AC current, then we calculate that G is the surface of the cylindric. If the DC for DC current, it is the cross section.
First of all, if this is a PEC, right? If this material is PEC, then the charge will only reside on the surface. That is the reason why you get the surface charge, surface current density. I repeat again. If this is a PEC, then the charge only exists on the surface of the material, and then that is how you get the surface current density. That is the reason. That is the circumstances where you apply this kind of thing on the surface, because there's nothing, no charge inside. Okay, this is hollow. But if this one is not a PEC, it is dielectric materials, then the charge can reside everywhere. That is how you get the J over an area, that is the cross section. Because there are some area on the core part that will reside charges. Okay. So let's go faster. So this is dielectrics slab. By introducing the kind of thing.
Page 39, I'm only there. Page 38 or 39.
I don't think this is going to be tested. Okay?
Only there.
Just one.
Even
Just reference only.
Okay. So boundary conditions I mentioned last class. Do I need to talk about this?
Yeah.
Yes.
Is that okay? Explain. Okay, no problem.
I skip or I explain.
Explain.
Explain. Oh,
Yeah.
explain. Okay. So let's see. This is tangential E component, right? Tangential E is parallel to the boundary. Normal means perpendicular to the boundary. Okay. So this is an area. This boundary conditions. I remember I I talk about boundary conditions. Boundary conditions. So first of all, this thing equals 0, no doubt, right? This thing.
Yeah.
This thing. And then the L, for this case, if the loop is written is like this, then the L can be divided into 4 parts. The L is this part, this part, this part, and this part. So, like, if I draw this kind of thing like this, if this is the boundary, and I draw the box like this. So this is LE, L2, okay, L1, L2, L3, and L4. Then I can write this as E1 dot L1 plus E2 dot L2. Right like this, right?
Okay, no problem.
Plus E4, L4, L4 equals to 0. No doubt about this, right? And then I just shrink. Again, I shrink this loop very thin so that L1 and L3 disappear. That they can be neglected. Okay? So L1 and L3 is gone. Right? Now I only have E2 dot L2 and E4 dot L4. So let's use these two. These two, this side part. But in that case, they use 1 and 2.
L2 and L4, yes. You're also using 2 only.
You
are correct.
use 1 and 2. So I write this as 1.
One, I understand.
I am afraid some of you might not.
1, okay.
Okay?
1.
Just first of all, what is boundary condition? Boundary condition is this one is your boundary, and this one is one kind of environment, and this one is another environment.
Two different
Yeah, just two materials. So they have like this one usually exists E1, and this one here exists E2, because they have two materials. Okay. So for this case, just I write it in a more rigorous way. So because I shrink L3 and L4 to be 0, then L3 and L4 will be gone. I only have L1 and L2, and because this is a loop, it has a direction. I have this kind of direction. I mean the L has directions. Okay. So now I have E1 dot L1 plus E2 dot L2. This is 0. Okay. And L1 and L2 has the same magnitude but the opposite directions. So L1 and L2, this kind of thing, I can synthesize in L out. Like I just write L1 and E1, E1 minus E2. Understand this? Dot L1. Okay, this one. This is because they have the same magnitude, but they are opposite directions. That is how I get this one. So that is how I get E1 equals to E2. Okay, just one more point to add. This one I can write E1 equals to E2. It's because I just assume that E1 and L1 has the same direction. If E1 and L1 doesn't have the same direction, then I cannot write them as E1. And if E1 and L1 has the same direction, E2 and L2 has the same direction, then the E1 is a tangential component. E2 is the tangential component. I repeat again. I can write it like this. I can write it like this, not because like this. This one is always holds. This one always holds. But I can write it like this based on the assumption that E1 and L1 has the same direction. Okay? And when E1 has the same direction as L1, L1 is what direction? L1 is like this. So which means I assume E1 is like this. Okay, and when E1 is like this, I call it as tangential E. Tangential E. That is the reason why he has a small t over there. ET component continuous across interface. That is just an interpretation to tell you. So I get that E1 and E2 tangential components are the same across the two materials. What is the physical meaning? That means the tangential E field is continuous across the boundary. When for this material, the tangential E field is like this, and when this kind of energy propagate along this boundary and come to the second material, then the E2 tangential, that means equal to the first one, it doesn't change. It doesn't change. When E1 tangential come across the boundary, come to the second material, the E1 tangential doesn't change. That is the meaning, what he meant. That he meant ET component, the tangential E is continuous across the interface. That's what he means here. Okay? Just how you remember this? You just remember, tangential E is the same beside the boundary. Right? They have two sides. If you have a boundary, then the tangential E here and tangential E here is the same. This is a boundary condition. Okay? Always holds. And we have a second boundary condition. Second boundary condition, which is just one thing. Okay, it is just basically this thing. For last case, the T means tangential. For this case, N means normal. So you can see the normal component of D1 minus normal component of D2 equals to rho S, that is charge density over an area. How can I interpret this? Okay, interpret this. You have a boundary, and this is D1 area, and this is D2 area. D1 normal is to D1 normal is in this direction. No, D1 normal is in this direction. Yeah, D2 normal is in this direction. When you and the discontinuous of these blocks can give you a certain charge that resides on the boundary surface. That is the physical meaning. So I repeat again. Discontinuity of the electric flux density can cause a charge on the surface. That is the physical meaning of this thing. And the boundary condition is very important is because they always hold. So when you're solving a certain problems, then you can apply the boundary conditions on the boundary, so that you can like to solve a certain very complicated problems. Okay? This is capacitance. Again, we can get a potential difference. That is delta V, so V1 minus V2, and this is a positive and negative Q, and we just define storage parameters. C equals to Q over delta V. I remember this one appears a lot in your examples. A lot of examples are based on this equation. So your lesson here is because I don't know whether you remember. For the examples over here, they have a very basic equation is this one. So when you do a problem that asks you about the capacitance, to calculate capacitance, first find the Q, second find the delta V. Okay? How do you find a Q? If you want to find a Q, you need to find D or E, right? This equation, right? If you wanna find Q, first you need to find a D, or you can substitute D as epsilon E. So you can also find E first, or you can find D first, then you can get a Q. That is how you get the denominator here. And then delta V is V1 minus V2. You remember we have a thing that is like this. point 1, point 2, right?
Mm.
So basically everything is based on previous conclusions, and then this is so much for the capacitance, this is the resistance. As far as I remember, this the example give you a lot of types or prototypes. For example, these types, and then here just and here is R, right? So this is how he get his R, and maybe you need this one, you do that. Maybe you need this one, so you can copy this one in your cheat sheet. You do not have to derive again. You can just apply the R directly. Just remember what is A, what is B, and how to calculate VAB, and then you can get a C or something. So very important is go through the example on the notes is very important, but also to remember the conclusion that is written on the notes. Then you do not have to derive again in your